Alright, this is going to be our third and final lecture for Module 3. In this lecture, we're going to be going over pool and junction boxes. This is going to be covered in Article 314, which starts on page 175 of your 2017 NEC. So, for objectives for this lesson, we're going to list the equipment considered for box fill. In other words, what type of things go into a box that affect how big the box has to be. We're going to use table 314.16a to select device boxes. We're going to use table 314.16b to determine the space required for conductors. And we're going to size boxes for 4 AWG and larger conductors. That's kind of the cutoff point for our boxes. We have different requirements for 6 gauge and smaller conductors, and different requirements for 4 gauge and larger conductors. Maybe a little bit reminiscent to back in Module 2 when we talked about identification methods for grounded conductors in Article 200. We had that cutoff line of different ways we could identify them. So the definitions for this lecture are going to be cubic, which is 3-dimensional. In other words, height, width, and depth is what we're going to be considering. And volume, the amount of space occupied by a 3-dimensional object as measured in cubic units. In other words, how much stuff can you put in a 3-dimensional object? You imagine we had a square dug in the ground. How much dirt would it take to fill that hole? So Article 314 covers outlet, device, pool, and junction boxes, conduit bodies, fittings, and handhole enclosures. Essentially, anything that we can put a wire or a device in that is not a panel board or a light fixture, some type of piece of equipment. So Article 314 covers requirements for pool junction device boxes and fittings used to connect raceways to them. The total volume of enclosures is the total assembled sections, including plaster rings, extension rings, etc. Where a barrier is used, the total volume will be distributed between these sections. So that 314.16a kind of told us 2 separate pieces of information there. The first being, once we've installed some type of enclosure or a box, if we add anything to that, whether it be a plaster ring or an extension ring, as they mentioned, anything we add to that box affects the volume, and it can either take away or add to. The second part being about this barrier idea. Maybe for some reason we need to install a barrier in a device box, whether it be to separate different voltages or maybe controlled wiring from line wiring. We have to distribute the volume of those sections evenly. So if it's a 100 cubic inch box and we put a barrier directly down the middle of it, then it's going to be distributed 50 cubic inches and 50 cubic inches. If we do it 60-40, it's going to be 60 cubic inches and 40 cubic inches. So looking at our first bit of a table here, we're going to be talking about table 314.16a. There's a couple different tables in 314 that we're interested in. Standard box volumes are listed in table 314.16a. Now, when I say standard here, we're usually going to be referring to a type of box. You could go to an electrical supply store or either a big box store like Lowe's or Home Depot, and you can just pick one of these up off the shelf. It's not custom made. It's not a custom ordered type of box. This is just your everyday typical use box. Boxes 100 cubic inches or less not listed in table 314.16a must be marked by the manufacturer to show their volume. So any box we have that's within that size realm, it should have a stamp from the manufacturer to show what the actual volume of it is. If the box is larger than 100 cubic inches, then we would just field measure out the dimensions of that box and then figure it ourselves. So looking at table 314.16a here, this table can look a little bit confusing at first, but once you break it down, it's not really that bad. On our left-hand column here, we can see the box trade size. So in other words, what that box is going to be commonly referred to as. And then we have our millimeters and inches columns. We're going to be sticking with inches, since I'm guessing that's what most people in this course are familiar with. And beside of that inches column, we can see the actual shape of the box. So we notice our first set of rows are for round/octagonal boxes. Then we have square boxes. Then we have device boxes. Then we have masonry boxes. In our next column over, we have the minimum volume. Once again, we have two different columns. We're going to be sticking with inches cubed. And then we also have a handy little section over here, which is the maximum number of conductors arranged by AWG size. So this is essentially kind of a cheat sheet to give you a quick number on how many of a certain size conductor you can put in a box. So the way we would use this box is first we need to establish, well, what type of box are we using? So for instance, say we're using a square box. A lot of this, if I had to guess, would be a type of box a lot of people would be very familiar with. We usually call them a 4-square box. We would look in our square section for the box with the appropriate depth we have. Obviously, a square box, it's going to be the same length and width. So the second dimension we have there next to the 4 represents the depth. So we have a 4-square box that's 1.25 inches deep, a 4-square box that's 1.5 inches deep, and a 4-square box that's 2 1/8 inches deep. We're going to go with that box. Next, we see that that box is allowable for up to 30.3 cubic inches of volume in total. In other words, we can put 30.3 cubic inches worth of stuff inside of that 4 by 2 1/8 inch box. Now, we could also approach this a different method, in that if we already knew how many conductors we were going to be using, we could then size our box based on that. So for example, if we knew for a fact that we needed to put 10 number 12 AWG conductors inside of a square box, then what we could do is in our far right column, the maximum number of conductors arranged by AWG, we can go to our 12 column, which is a 12 gauge conductor, and then move down until we see a box large enough to contain 10 number 12 gauge conductors. So moving down to the square section, since I said we want a square box, I can see that a 4 1/4 inch square box can only hold up to 8 number 12 conductors. Moving down to a 4 1/2 inch square box, I see that it can only hold 9. Now once I move up to 4 2 1/8, I see it can hold up to 13 number 12 AWG conductors. So we could use that box. Moving down from there into our 4 11/16 boxes, I can see that those range from 11 all the way up to 18 number 12 gauge conductors. So I could use any of those sizes of 4 11/16 boxes that are here in table 314.16a. So those are two different approaches on how we could use this. In our first situation, we looked at if we already have the box installed and we need to know the total volume amount of it. In our second example, we looked at if we already knew how many conductors we needed to put into the box and we wanted to select a box based on that. Moving on from there, we're going to be getting into how we actually do our calculations to see how much stuff it is that we need to put in a box now. So 314.16b1 through 5 must be added together to calculate the total fill based on the largest conductor present. In other words, we have a list of items that are covered in 314.16b1 through 5. We have to work through all 5 of those steps and add them all together to figure out how much stuff we have going in this box. Once we have that final number, we're going to size that based on the largest conductor in the box. And this will become a little bit more clear as we work through the steps. So for B1, we're going to make one allowance, and you can think of an allowance as a count or as a wire. Essentially, every allowance is going to take the place of one wire in this box, because that's how much space it needs. So one allowance for each conductor that originates outside the box and terminates or splices in or passes through the box. So if we have a conductor that comes from outside the box and it goes inside the box, essentially we're going to count it. Because if it comes from outside the box and goes into the box, we're either going to terminate it, we're going to splice it, or we're just going to pull it straight through the box. And according to B1, in any of those circumstances, we have to count that conductor at least once. Now, the little bit of, not per se an exception, but the caveat to this rule is a conductor that originates in the box, such as a jumper, we do not have to count those conductors since they originate inside the box. B2, we're going to make one allowance for one or more internal cable clamps, and the one or more is a very important key note here. So regardless of how many internal cable clamps we have inside of a given box, we're only going to make one allowance count for all of the cable clamps. It doesn't matter if we only have one cable clamp or if we have 10 cable clamps, we're only going to count them one time. B3, we're going to make one allowance for one or more luminaire stud or hickey. And what this is referring to is, for those of you that installed mainly a residential type light fixture, these luminaire studs or hickeys come from the manufacturer, and you secure them to the box in order to attach the light fixture to, mainly the globe of the light fixture for surface mounted light fixtures. So once again, the same as our cable clamps, if we have one of them, we count it one time, but it doesn't matter if we have 10 of them, it's still only a one count. B4, two allowances for each yoke or strap containing one or more devices. So for those of you that have worked with a standard duplex or a single pole switch, three-way switch, four-way switch, you know that the tabs that those devices mount to the box with are called a yoke or a strap. For each one of those we have, we're going to count that device one time. Now note what this means is that if we have a duplex receptacle, which is two receptacles, we're still only going to count that twice, even though it is two devices. It's only one yoke or one strap. The same thing as if we had a set of stack switches, which are two switches, one on top of the other. Even though that's two devices, we're still only going to count it as two allowances, even though it's two devices. And this is because it has only one yoke or one strap. But that is important to note that it is a two allowance count, not a one allowance count for each yoke and strap. And then finally for B5, we have one allowance for one or more equipment grounding conductor or conductors based on the largest equipment grounding conductor present. So B5 is a little bit of a standalone point in my opinion, in that we're going to size the allowance required by B5 based on the largest equipment grounding conductor, not the largest conductor in the box. In other words, we could have a number 10 current carrying conductor in the box, but if our largest equipment grounding conductor is only a number 12, then that's what we're going to use for our allowance on B5. So here's a picture that kind of visualizes all of these steps that I'm going to talk through with you all just a little bit here. So starting at the top here, we can see that we have a 14.2 and a 14.3 cable entering this box. Now 14.2 obviously contains a ungrounded conductor and a grounded conductor. We're not worried about the grounding conductors at this moment, just the current carrying conductors. So that gives us a count of two conductors, and then our 14.3 is going to carry three more current carrying conductors for a total of 5 conductors. So in other words, this would be 5 allowances. Next we see we have 2 internal cable clamps for those cables. Once again, regardless of how many cable clamps we have, we count the total number of them as only 1 allowance. So even though there are 2 internal cable clamps, we only need 1 conductor or 1 allowance. Next, we see kind of in the middle towards the bottom of this diagram, we have 2 ground wires. And once again, regardless of how many equipment grounding conductors we have, we're going to count all of them one time based on the largest equipment grounding conductor present. So this equals 1 conductor or 1 allowance. And then finally we see on our left and right hand sides we have a single pole switch and a duplex receptacle. The single pole switch being one device mounted on 1 yoke or strap, we count that as 2 conductors or 2 allowances. Our duplex receptacle being 2 devices mounted on 1 yoke or strap, we're still only going to count that as 2 conductors or 2 allowances, meaning that our total count of allowances for this box, not counting the equipment grounding conductor, would be 10 conductors. Counting the equipment grounded conductor, that would bring us up to 11 allowances. And an important note down on the bottom right hand side of the picture is that wire connectors and pigtails do not count. In other words, whether we're using a wire nut or some other type of termination device in the box, maybe a lug or otherwise, those don't count, as well as I'd previously mentioned. Conductors that originate in the box and terminate in the box also do not count towards this allowance amount either. So from there, now that we've kind of added up and counted how many allowances we need to actually know how much we're going to include for each of those allowances. So once 314.16b 1 through 5 have been accounted for, the volume for each allowance must be selected based on table 314.16b. All allowances other than B5 will be based on the largest conductor present in the box. B5 will be based on the largest equipment grounding conductor present in the box. So in other words, in our previous slide we looked at, I said there was an allowance amount. There was a total of 10 allowances, not counting the equipment grounding conductor, and then one additionally for the equipment grounding conductor. And here is table 314.16b. Try to keep those numbers I previously mentioned, the 10 allowances plus one equipment grounding conductor, in mind. We have, and once again, table 314.16b, volume allowance required per conductor. This is a very straightforward table to use. On the left-hand column, we have the size of the conductor in AWG. And then on the right-hand column, we have the free space within the box for each conductor. Once again, we're going to be looking at the inches squared, or cubed, column. And we can see that if we start with an 18 gauge conductor and go straight across that row, we have 1.5 cubic inches for an 18 gauge conductor. Moving down to a number 12 AWG conductor, we can see we need 2.25 cubic inches per number 12, and then down to a number 6 AWG, we need 5.0 cubic inches per conductor. So on our previous picture we looked at, I said there was a total of 10 allowances. Now our largest conductor we had in that box was a 14 gauge conductor because we were using 14.2 and 14.3 cables. So for those 10 allowances, we would go to our 14 in our size of conductor column and go straight across that row to our 2.0 cubic inches. Then we would just multiply our 10 allowances by our 2.0 cubic inches and get a total of 20 cubic inches for everything except our equipment grounding conductor. Now, assuming those cables had a 14 gauge equipment grounding conductor with them, we would only need one allowance for that. Once again, basing that on a 14 gauge conductor, that would be an additional 2 cubic inches for a total of 22 cubic inches. So let's work through a quick example of how we would do this for, say, a test question or a real-world example. So we have a box that contains two 14.2 NM cables, one 12.2 NM cable, 3 sets of internal cable clamps, one single pole switch, one duplex receptacle, and 3 wire nuts. So this means that in total, we're going to have 3 ungrounded conductors and 3 grounded conductors. Since each 14.2 and each 12.2 NM cable contains one ungrounded conductor and one grounded conductor, that would be a total of 6 allowances. Next, we have 3 internal cable clamps, and once again, regardless of how many internal cable clamps we have, we're only going to count them one time, so that would be a total of 1 allowance. Next, we have 2 devices with 2 device yokes or straps, the single pole switch having 1 set of yokes and straps, or straps, and the duplex receptacle having 1 set of yokes or straps. That would be a total of 4 allowances. Next, we have 3 equipment grounding conductors, since each 14.2 and each 12.2 are going to have 1 equipment grounding conductor. That would still be, though, a total of 1 allowance for the equipment grounding conductors. And then, of course, we do not count the wire nuts towards our allowance. So this gives us a total allowance of 11 plus our 1 equipment grounding conductor allowance. Continuing on with this example, we see that the largest conductor in the box was a number 12 because we had two 14-2s and a 12-2. So going to table 314.16b, the space for a number 12 conductor is 2.25 cubic inches. 2.25 cubic inches times 11 allowances equals a total cubic volume of 24.75 cubic inches. And we're assuming that our largest equipment grounding conductor in the box was also a number 12 gauge conductor. Using table 314.16 again, once again, the space for a number 12 conductor is 2.25 cubic inches. 2.25 cubic inches times 1 allowance equals 2.25 cubic inches. So the total volume required are 24.75 cubic inches for all of our normal allowances, plus our 2.25 cubic inches for our equipment grounding conductors equals a total allowance of 27 cubic inches for the box we previously talked about. Moving on from these box fills and calculations and whatnot, we have some general requirements for weight ratings on outlet boxes that I wanted to cover very briefly on this slide. Boxes used to support vertical mounted luminaires must be marked to show the maximum weight it can support if that weight is other than 50 pounds. So for a vertical mounted luminaire, this vertical obviously being up and down, so essentially a wall mounted luminaire. If the box that we place in that wall or other vertical surface can support any weight other than 50 pounds, then it has to be stamped to state what weight it can hold. For ceiling mounted outlets used for lighting, they must support a minimum of 50 pounds. So if we're mounting a box in the ceiling or on the ceiling in order to support some type of light or luminaire fixture, it has to be able to hold at least 50 pounds. Floor boxes, so any type of device box that's going to be installed in the floor, must be listed to be used for that application. In other words, we can't just take a standard device box and install it in the floor for that use. It has to be specifically listed for use as a floor box. And finally, boxes used to support fans must be listed and not support a fan more than 70 pounds. In other words, a box we're going to attach a ceiling fan to has to be listed as suitable for that use. In other words, it has to be a fan rated box, and we can't use that box for any fan that weighs more than 70 pounds. We would have to have a box listed for more than 70 pounds, and the general fan rated box is not listed for more than 70 pounds. So as I said, those were just some quick weight ratings I wanted to talk about before we got into our pull box sizing for our 4 gauge and larger conductors. Since, as I had mentioned previously, we have a different set of requirements for pull boxes used for 6 gauge and smaller conductors and 4 gauge and larger. If you paid attention to your table 314.16b, you may have noticed the volume allowances for that table stop at a 6 gauge conductor. Once again, to stress the point, that's because we have this different set of rules when we're using 4 gauge and larger conductors. So pull and junction boxes connected to raceways containing 4 gauge and larger conductors must meet 314.28A1 and A2. So we have 2 different sets of requirements here. So A1 covers straight pulls. So for straight pulls, the length of the box must not be less than 8 times the largest raceway. So if we're using a box to pull a conductor straight through the box, whatever the size of the raceways are in that straight pull, the bigger of the two, we have to multiply that by 8, and that's going to be the dimension of that box. A2 covers angle U-pulls and splices. So anytime we're making an angle pull, a U-pull, or a splice pull, we're going to be going to A2. The distance between the raceway and the opposite wall must not be less than 6 times the largest raceway plus the diameters of the other conduits in that same row. And we have a picture on our next slide where I'll talk about this in a little better detail, since you'll have a kind of a visual representation of what we're talking about. Also, part of A2 tells us the distance between raceways enclosing the same conductor must be at least 6 times the larger of the raceways. So we have 2 raceways enclosing a conductor where it's set up to be in an angle, U-pull, or a splice. They have to be at least 6 times the larger of those 2 raceways apart. And once again, I'll talk about that a little bit more on our next slide. So for our visual representations here, on our left-hand side, we see we're talking about A1 for a straight pull. So we see for this picture, we have a 3-inch raceway entering the box and a 3-inch raceway leaving the box, and we're making a straight pull between the 2. So all we're going to do in this situation is take the largest raceway, in this case they're both 3-inch, and multiply that by 8. So we can see the distance between these 2 raceways equals 24 inches. And it really helps to kind of understand the mindset of why we want this. The idea is that we want enough space so that once we pull those conductors in through the first raceway, we can bend them back down and pull them out through the second conductor, the second raceway. You have to keep in mind, if these raceways were only 2 inches apart, you're not going to be able to bend that wire tight enough without damaging it to pull it into the second raceway. So we want that distance between them in order to do that without damaging the conductors. Moving on to A2, on our second right-hand side here, we see that in this particular situation, we have 2 separate rows on the side of this enclosure. We have row A1 and row A2. So for row A1, we have a 3-inch raceway and 2-inch-and-a-half raceways. For row A2, we have 3 1-inch raceways. And then at the bottom here, we can see the math for how we would do this. For row A1, we have 6 times the largest raceway in that row, which is a 3-inch, plus our other raceways, which are 1.5 and 1.5. And this equals out to a total of 21 inches. For row A2, we take our largest raceway, which is a 1-inch, and multiply it by 6, plus our other raceways, which are a 1-inch and a 1-inch, and we get a total of 8 inches. Since 21 inches was our larger dimension for that side of the box, the distance from those raceways on that side of the box to the opposite wall, which is represented in the box by the figure A, has to be at least 21 inches, assuming we're going to be using those raceways for an angle or a U-pull, which you can see somewhat depicted inside the box as well. We're going to be pulling from the bottom of the raceway into the side raceways. Now, for our little side note about the six times the larger of the 2 raceways for our distance between, essentially what that means is that assuming we had the same conductor being enclosed by raceways on the side and raceways on the bottom, we would need the physical distance between those raceways to be 6 times the larger of the 2. In other words, for our front row A2, if we assume that we had a conductor in one of the 1-inch raceways going into the raceways on the bottom, and those were also 1-inch raceways, then those raceways would need to be 6 inches apart if we pulled a tape measure across them inside the box, since they enclose the same conductor. And that's all that little side note of A2 is talking about there. So that concludes this lecture, and it also concludes our lectures for Module 3. In our next session, we're going to be starting off Module 4 with Cable and Raceway.